So say you want to solve an elastic collision in one dimension. So a little bit like the cart problem that we've got going on in lab. You have a little blue cart and a little red cart, and they're on a track, and they're only allowed to move on the track, so it's only one dimensional. And we set it up so it is actually elastic. So before the collision, maybe this blue one, we'll call that mass 1, is moving at some initial velocity, so we'll call that v1, and then I for initial. And the red one over here, it's got some mass, we'll call it mass 2, and it's got a velocity initially, so we'll call that v2I, again, I for initial. So say they're just going the same way. If one of them is flipped around, I guess we could just change the sign on its velocity because it's one dimensional. We don't have to worry about components. So what happens afterwards? Well, we'll still have our two carts. It's an elastic collision, so they're not going to stick together, so they'll both just keep their mass. But who knows what speed they're going? So we'll just have velocity 1 final. Didn't write that very clear, so let me write it more clearly. v1f for the final velocity for the blue cart. And then for the red cart, m2, we'll call that v2f, and we don't know what that is. Maybe we're able to measure these two velocities and we know the masses, but we don't know the final velocities. How would you go ahead and solve this? Well, it's not simple, even if you're pretty comfortable with the concepts. So what are the things we know about the situation? So we're going to assume, well, first, we're going to assume momentum is conserved. Maybe we're told that explicitly in the problem. Maybe we can see for ourselves that the external forces on this system add up to 0. Maybe we can even, kind of do a little bit of our cheat way of doing this, which is to say the change in momentum is the impulse, which is equal to the net force, or the average force on it, times the time over which that force acts. So if we don't really have that the net force is equal to 0, we can look right before the collision and right after the collision and make this delta t as small as possible. So we're doing one of those things. We're going to assume the momentum is conserved. So after the collision, we're going to have the same momentum of the system that we've got before. So this means that the change in momentum is 0, so the momentum of the system initially before the collision is going to be the momentum of the system finally at the end. We're also told it's elastic. So that tells us that the kinetic energy doesn't change. And that means that the kinetic energy initially is equal to the kinetic energy at the end. So these are the two things we know. 1, we're going to assume momentum's conserved, and 2, we're told right here that the collision's elastic, so kinetic energy is conserved. What can we do with that? Well, with momentum, if we know that the initial momentum equals the final momentum, we can just write out what the momentum is before and after the collision. So before the collision, it's mass 1 times its initial velocity, v1I, plus mass 2 times mass 2's initial velocity, v2I. So that's my initial momentum, and it's equal to my final momentum. I don't know what these velocities are, but I've written down symbols for them, so I can at least write them into my equation. Mass 1 times mass 1's velocity, the final, and then mass 2 times its final velocity. So that's what we get from momentum being conserved, and over on this side of the equation, that's the final momentum. We're also told that the kinetic energy is conserved. So let's write that down. The initial kinetic energy is equal to the final kinetic energy. So what's the initial kinetic energy? Well, 1/2 the first mass times its initial speed squared plus 1/2 the second mass times its initial speed squared. So that's all the initial kinetic energy. The final kinetic energy is mass 1 times its final speed. We don't know what that number is, but we got a symbol for it. So we'll go ahead and use it. And then also the kinetic energy of the second mass after the collision, which is 1/2 m2 v2f. So this over here, that's going to be our final kinetic energy. All right, so in theory, we can solve this, right? There are two things we don't know. So we're told these initial speeds and we know the mass. If we don't know the two final speeds, well, that's two things we don't know, the final speed of mass 1 and the final speed of mass 2, two unknowns, but we have two distinct equations. So we should be able to solve that. But because of these squares, it's not very simple to do that. So what do? Well, the first thing I'm going to do is I'm actually going to put all of the mass 1 stuff on one side of the equation and the mass 2 stuff on the other side. So that means my momentum equation is going to become this. I'll have mass 1 times v1I, and then I got mass 1 information over here, so I'm going to move it to the other side of the equation. So it'll become negative mass 1 v1f, the final velocity. Then I'm going to do the same thing and move all of the m2 stuff over to the far side. So mass 2 v2f minus mass 2 v2I. Got a little close to the edge of the paper there, that's all right though. Now I'm going to collect the masses. So I just collected m1 off of these terms. I'm left with the difference from the initial to the final speed. Do the same thing over here for mass 2. Get mass 2 times the quantity v2f minus v2I. All right, and maybe you have no idea why I'm doing this. And it's kind of a weird thing to do, I will admit. But let's continue on. Let's do the similar thing down here with our kinetic energy. Let's collect all the mass 1 stuff on one side and all the mass 2 stuff on the other side. Well, I guess the first thing I'm actually going to do is I got a 1/2 in every single term. So I'm going to go ahead and cancel those 1/2s. Because I got 1 in every term, so I can cancel them out. All right, now having done that, I am going to move all the mass 1 stuff to one side. So I'll have to subtract this term right here over to the other side. And then move all the mass 2 stuff over to this side. So I've got mass 2 v2f squared. So this term, I'll just move it right here. This term is over on the wrong side, so I'll need to subtract it. So minus m2 v2I squared. All right, so now I got mass 1 stuff on this side of the equation, mass 2 stuff on this side of the equation. And why did I do that? Well, let's do the same thing we did with the momentum equation here. Let's pull the mass 1s out. So we'll be left with v1 initial squared minus v1 final squared. That quantity times mass 1. Same thing on the other side. Mass 2 v2 final squared minus v2 initial squared. And if you had been forced to factor a whole lot of equations when you were younger, like I was, you might see that this is a perfect square. We got 2 perfect squares here. And that's actually what we're going for. Because when you have perfect squares, you can factor them. So v1 initial squared minus v1 final squared, that's going to be v1 initial minus v1 final. That quantity times v1 initial plus v1 final. And then let's double check that that actually makes sense. So if I multiply these 2 first terms, v1 initial and v1 initial, I get v1 initial squared. If I multiply the 2 last terms, negative v1 final and positive v1 final, I got negative v1 final squared. And then if I look at the 2 cross terms, these inner terms, I get negative 1 final times 1 initial. and positive 1 final times 1 initial. So those will cancel. So this guy is how you factor this side of the equation. And the same thing will happen over here. I got my 2 final minus my 2 initial, and then my 2 final plus my 2 initial. So we just factored this perfect square here. All right, and this is why I was actually doing what I was doing. So this guy is the kinetic energy equation. So let's just remind ourselves. That's kinetic energy equation. Up here, that's the momentum equation. And if you take a look, we got M1, V1 initial minus V final, V1 final right here, and M2, V2 final minus V1 initial. So here, right there, is our momentum equation within our kinetic energy equation, because we were factoring these two perfect squares. So now I'm going to do something really very odd. I am going to divide my kinetic energy equation by my momentum equation. So I got M1 V1 initial minus V1 final times V1 initial plus V1 final. That's one side of my kinetic energy equation. The other side is M2 V2 final minus V2 initial. That quantity is all times M1, and then we have V2 final plus V2 initial. That's the other side of my kinetic energy squared. And now I'm going to divide it by my momentum equation. So I'm dividing this side by M1, V1 initial minus V1 final. And I'm going to divide by the exact same quantity over here. I'm just going to write it differently, because whenever you do something to one side of an equation, you have to do the same thing to the other side. So I'm going to divide it by this, but I'm going to divide it by this in a different way. I'm going to divide it by this side of the equation. So I'm doing the exact same division. I'm dividing by the exact same number, because I know that this M1 times the quantity V1 initial minus V1 final is equal to M2 times the quantity V2 final minus V2 initial, right there. And then I can cancel all kinds of stuff. My M1s cancel here. This quantity cancels with that quantity. Over here, my M2 cancels, and then that quantity cancels with that quantity. And I am left with this. Which maybe doesn't seem like an improvement to you. But say I want to solve for the final velocity of mass 1. So in that case, I'm going to actually isolate this guy and then substitute it into my momentum equation. So when I isolate it, I will get V1 initial plus V1 final minus V2 initial. That'll equal to the final velocity of the second mass. And now I can substitute that back into my momentum equation. Let me rewrite my momentum equation. M1, and I think I'll go back and I'll rewrite this chunk here. M1 V1 initial minus M1 V1 final equals M2 V2 final minus M2 V2 initial. And I'm just going to sub that in right there. M1 V1 initial minus M1 V1 final equals M2, and then all of this subbed in for V2 final. V1 initial plus V1 final minus V2 initial. We've got in all of that stuff. Now for the very last term in this equation, M2 V2 initial. Now I need a little more space, so we'll just scoot this up here. And what was I doing again? Oh, right, I was solving for V1 final. So let's get these two V1 final equations on their own. All right. move my paper a little bit. So I'm going to do M1. All right, I got that. Let's see, maybe I'll distribute this M2 first. So we got M2 V1 initial plus M2 V1 final minus M2 V2 initial. So I've just distributed this M2 to these three terms and then rewrite this last term, M2 V2 initial. Oh look, we got two of those. Very nice. They don't cancel though because they both got the same sign. All right, so now we're going to get all of the V1 final off to one side because that's what we're solving for. So I'm going to move this guy over to the other side. So I'll have M1 V1 initial. Nothing happens to that. It can stay where it is. This one gets subtracted over here. M2 V1 initial. Let's see, this one can stay where it is. We'll move these two over. So we'll get minus M2 V2 initial. There's minus over here. I guess it's plus when it goes to the other side of the equation. Same with this guy. And then we got M2 V1 final. All right, let's see, make sure we got all of our terms. This one was here. It was positive on this side, so it's negative over here. This one is negative over here, so it's positive over here. This one's negative over here, so it's positive over here. That one didn't move, but this one we've got to move over. So it's negative on this side. It'll be positive when it gets over here. Okay, and I guess we can maybe combine things a little bit. Let's do M1 minus M2, that quantity times V1 initial. There are two of these guys, so we'll just write it as 2 M2 V2 initial. And over here, we'll collect our V1 final, so we'll mush the masses together, M2 plus M1, or I guess we could write it M1 plus M2, doesn't matter because addition can be done in either order. And then we'll just divide by this. So divide by M1 plus M2, same thing as M2 plus M1, got to do it on both sides. And I guess let's split up the two terms. So we'll have M1 minus M2 over M1 plus M2 times the initial velocity of mass 1 plus 2 times M2 over the sum M1 plus M2, the initial velocity of mass 2, and then here those terms cancel and we're left just with the final velocity of mass 1. So that was an awful lot of gross algebra. And I will say that I highly recommend that you go find the expression for the final velocity of the second mass, doing the same thing that we just did. You can start from here and then sub into the momentum equation. But I can actually figure out what it's going to be by just saying, when I look at these two masses, the only thing, there's no reason to kind of choose between them, particularly since we're in one dimension, and if we switch the velocities, they just change signs. So all I really need to do to figure out what's going to happen is swap all of the subscripts here. Everywhere I see a 1, put a 2. Everywhere I see a 2, put a 1. And that's going to get me my final velocity for mass 2. So you see what I'm doing is I'm just copying down the exact same equation, just everywhere that there was a 1, I'm writing a 2, and everywhere there was a 2, I'm writing a 1. Except for that 2, of course, because it's not having to do with the masses, it's having to do with the fact that that is an actual number 2. So we'll leave that one be. Oops, and that should be V1 initial. So this will be what's going on with the second mass. So these are for a one-dimensional elastic collision where momentum is conserved. And you can use them anytime you've got this set up. It's one-dimensional, it's elastic, so kinetic energy is conserved, and momentum's conserved. And I guess you can only do it with two masses, because that's all we got. But once you know this, you're all set. But it was a lot of algebra, so let's double check that it's going to make sense in a couple of instances where we know the answer. So we just wrote down, this is true for any two masses at any old speed. We know what's going to happen where we have a situation, so we're going to check our answer. If mass 1 equals mass 2, that is, they're the same mass, and initially the first or the second mass isn't moving. So in that case, we've got one mass is coming in this way with some initial speed, and it's going to hit a stationary second mass. And if the masses are equal, that'll be before the collision. What happens after the collision? Well, as you probably remember from just playing around with the carts or watching what they do, our first mass will stop, and then our second mass will take off with that exact same speed in the other, in the same direction. So basically this mass is just going to pass all of its momentum off to the second mass. It'll come to rest and the second mass will take off. Let's see if our equations say that's what will happen. All right, so if our masses are the same, we're expecting this first mass to come to rest. So we're expecting the final velocity of mass 1 to be 0. So the masses are the same, so we'll just put in m. So m minus m right here, that's going to be 0. And then here 2, that's m2, that'll just be m over m1, that's just m, m2, that's just m because they're the same mass. And initially that second mass isn't going. So m minus m, that's 0, which means this whole term is 0, and then anything times 0, that's 0, so yeah, that'll be 0. That checks out. That's what we're expecting. Oh, and I'm drying off there. So what we had here is m minus m, the mass is the same, this first term is 0, and here the second velocity, initially that velocity is 0, so this term is 0, so both terms are 0, so the first mass after the collision, it doesn't move. Now let's check and see what the second mass does after the collision. We're expecting it to just have the initial velocity of the first mass, so let's see if that's what happens in the equation. All right, here's the equation for it. These masses are the same, so we'll just put in m for both masses. Here we go, wrote this term, just put in m. v2 initial, that's 0, so we'll plug in a 0 for it, plus 2 times mass 1, that's m, over mass 2, that's m, plus mass 1, that's m, and the initial velocity of the first one. All right, so this is m minus m, that's 0, but we're multiplying it by 0, so this term is 0, kind of doubly 0. This term is 2m over m plus m, that's 2m, times the initial velocity of the first mass. Well, 2m over 2m, those both cancel, and we're just left with the initial velocity of the first mass, which is what we expect. So even though we did a lot of algebra, it looks like these guys work, at least for a case where we know what the answer should be. And like I said, you can now use these equations anytime you have this kind of a situation. And I do strongly suggest that you go through and do the algebra yourself just to get the practice with this technique to find this second final speed of the second mass.